if you wanted to make more money in your lifetime, if you wanted to increase your lifetime earnings, well, you know just intuitively that you can try to make more money every year, so you can increase your annual income. That might involve taking a second job or going into a field that's more lucrative than architecture, or you can work more years. So you could put off retirement a little bit longer, or you could try to graduate high school a little bit earlier. Either way, if you double your annual income, you double your lifetime earnings, or if you double the number of years you work, you also double your lifetime income, lifetime earnings. All right. Now, likewise, if you are watering your lawn with a hose, the amount of water coming out in gallons per minute is going to be a function really of two things. One is the pressure in the hose, and one is the diameter of the hose, the flow. How big is the hose? So if we wanted to double the amount of gallons per minute, we could double the pressure. Or if we wanted to double the gallons per minute, we could double the cross-sectional area of the hose. Or if we did both, we would increase it by 4. Now, just like with annual income, there's some advantages to earning more and some disadvantages, like you're working 2 jobs. And there's some advantages to working more years, like you get more money over your lifetime, but there's some disadvantages, like you might not enjoy retirement as much. Well, likewise, with the hose analogy, if we add more pressure, it may kind of bust the fixture, it may bust the nozzle we have on it. And if we increase the size of the pipe without adding more pressure, we might not be able to throw the water as far. So there are reasons to kind of lower or increase the pressure. There are reasons to kind of lower or increase the flow. Likewise, if we're talking about electricity, we say that watts, which is our power, that's what we need to actually run our appliance. That's what you guys are using now or used before to charge up your appliance, charge up your whatever you're using, whatever device you're using to listen to this on and watch this on. So that watts is equal to the voltage, which is the electrical pressure. In fact, 125 years ago, voltage was called electrical pressure. So it's how hard those electrons are being pushed times the current, which is a function of the diameter of the pipe. So it's the diameter of the wire. So to get more watts, to get more power to your device or to your dishwasher or to your air conditioner, we can increase the voltage. We can double the voltage. That will double the watts. That's more, you're pushing it more. Or we could double the current. We could double essentially the cross-sectional area of the wire, and that would bring more electrons as well. And if we did both, we would double the voltage and double the current. Then we would multiply the total power by 4. All right. Now, welcome to Amber Book, 40 Minutes of Competence. Now, why do we care how much voltage there is or how much current there is? And voltage, of course, is pressure, and current is wire diameter. So why do we care if we have too much voltage? Well, if we have too much voltage, we tend to risk electrifying ourselves. So we're more likely to get shocked when we plug it in. We're more likely to get hurt that way. If we have too much amperage, if the wire size is too big, especially over long distances, but even over medium-sized distances at some wire size, we risk the wire heating up and causing a fire. So we want to balance the risk of electrical shock with the risk of fire, and we want to between the two kind of hit a sweet spot. All right. Now, once you kind of own that, we can go back to our question. And our question was, what type of power delivery is this circuit? And you see the circuit this is a breaker box, and a breaker is overcurrent protection. And so it's doing two things. One is it's taking power in and it's distributing it. So it's saying you, electron, in this branch circuit, and a branch circuit's like the final circuit in the series, right before it goes to your, your 3, well, let's say this one, you branch circuit, go to these 3 electrical receptacles and go to these 4 light fixtures. and you, this one, you go to the coffee maker, and you, this one, you go to the specialized microscope equipment that we're using in this particular building. And then you, this guy, that's when we're asking about where these three are getting together, you're going to go somewhere special. Now, this particular circuit, to give the answer to the question, this circuit, well, there's really two correct answers that I will accept. One is it could be 120 volt / 208 volt, 3-phase, 4-wire. That's actually what it is. But you could have said, because you wouldn't know any differently, it looks the same. You could have said it is 277 volt, 480 volt, three-phase, 4-wire. Either one of those, if you got it right, you are correct. All right, let's talk about what it is that that differentiates these different flavors. And really, and remember, it's all about bringing power that is safe and smooth. All right. So what's going to happen is we're going to bring in power from the power company. So from the wire, we're going to bring it in and we're going to send it through a transformer. Now, maybe it comes in at, I don't know, 12,000 volts or something like that. But the transformer is going to step it down. And in this case, we're dealing with a house. This first example is for a house. And so that transformer is going to send 3 wires into the house. That transformer may be on the ground outside near the front lawn. It may be up in a pole. In theory, it could be inside the house, although that's a little less common for single-family detached residential. But it's sending in a hot 120 volt wire. It's sending in a second hot 120 volt wire, and they're in phase, importantly, and it's sending in a neutral. Now, these wires are then going to go into a circuit breaker, kind of like what we just drew. And that circuit breaker is not only going to distribute the power to the different branch circuits, telling the electrons, you go over here and you go over there, but it's also going to provide overcurrent protection. So if there is a situation and the wire gets too hot, there's a short circuit, then there's going to be a little switch in the circuit breaker that's going to flip off. So those switches, we'll draw one here. They kind of insert, they're a little bit like a tooth. They go way back. You don't see the part that goes back, but it's got a little switch and that one's on. And out of that switch is going to come two wires. There's going to be a hot 120 volt wire, and there's going to be a neutral. All right. Now, this circuit, we'll say it goes to, what do we say, 3 electrical receptacles and 4 light fixtures. So here's an electrical receptacle it's going to, and we'll take our blender. We'll take our blender and we'll go ahead and plug it in to this electrical receptacle. And the electrons are going to go out through the blender motor and then back. But actually, because it's alternating current, they're going to go back and forth. Because with alternating current, and with current in general, it's not really about the electrons that are moving through. It's about the rate that the electrons are moving through. So you just got to keep moving them through. But you're allowed to move them back and forth. If you have equipment that knows what to do with electrons moving back and forth, we're going to, it's AC or alternating current, we're going to move the electrons back and forth. All right. Now, we're going to have another circuit on this house, and this one's just going to do all the lights in the bedrooms. All right, so this one also is going to have hot 120 volt wire coming from it, and it's going to have a neutral. And this one is going to go to the light fixtures in the bedrooms, and it's going to bring us light. Now, we also have some bigger appliances. So we have our stove and our oven, and we have our air conditioner unit outside, the condenser compressor unit that sits outside that looks kind of like this. Let's see what it looks like. It looks like it's got like that, and it comes out. It maybe sits on a pad. Maybe it's got a grill right there. Anyhow, that's a little thing that sits on a pad outside your house if you have a single family detached house. And that, because it has a compressor in it and it's the air conditioner and it needs a lot of juice, we don't want to just send one hot 120 volt to it. And the reason we don't is if we do that, remember that the power that it uses is equal to the volts, which is the pressure, times the current, which is measured in amps, which is the wire size. If we only send 120 volts, we only send one wire with 120 volts and a neutral, then we won't get enough oomph. We won't get enough oomph to make this thing go without sending a whole lot of heat down this wire. So we need a second wire so it doesn't overheat. So we're going to send 120 volt hot and another 120 volt hot and a neutral. And together we can add them together and we can make 240 volts. So really what's happening is if we were to map the electrical pressure, the voltage, it's a sine wave. We're sending the electrons forward, then we're pulling them back, then sending them forward, then pulling them back, then, so if this is kind of the speed of the electrons, everything above that line, the electrons are moving forward, and everything below that line, they're moving back. And on the x-axis is time. And so we're sending the electrons forward really hard, and then we're yanking them back really hard, and we're sending them forward really hard and back. And how hard we're sending them is, for each of those two wires, is 120 volts. So 120 volts doesn't mean it's continuously that much pressure. It means that's what we're maxing out at. We are maxing out at 120 volts. And so this particular flavor of power is called 120 volt / 240 volt single phase. And we call it single phase because both 120 volt lines here are pulling and pushing the electrons together. They're pulling and pushing together. I don't know, like a crew team in an elite boarding school. They're all rowing at the same time. And so we call that single phase because they're in phase with one another. They're both pulling and pushing at the same time. And because there are three wires going into the house, one hot 120, one hot 120, and a neutral, we call that a three wire, this particular flavor of service. And just about every house that's single family detached has this flavor of power delivery. All right. Now, if we have, let's say it's a drugstore, so we have something bigger than a house, but smaller than a large office building, smaller than a hospital, smaller than a very large campus building, et cetera, like a community college campus building. So in that case, we have typically three wires going into the transformer. And in that case, the transformer may be, and again, maybe it's 12,000 volts. And what's going to come out of that is going to be four wires, 120 volt hot, a second 120 volt hot, a third 120 volt hot, and a neutral. And that transformer is stepping it down from 12,000 volts. Now, it depends on your municipality. That 12,000 number is a number I made up because that's what we have here. We're in the building I'm in, or in the city I'm in. But that number could be 3,000. It could be 60,000. It's typically going to be somewhere in the order of I don't know, 5 to 10,000, depending on where you live. Anyhow, that transformer is going to step down that power. And then that transformer may be in the building, it may be next to the building, it may be on the pole, and it's stepping down the voltage of the power. Oh, going up here, I forgot to draw this one. So this particular, sorry to shift gears, but we're going back to the 120 volt, I'm sorry, the 240 volt circuit that's going to the air conditioner and the cooktop and the other big equipment in the house is actually going to be 220 volt circuit breakers ganged together like that. And you probably have seen them in your breaker box. That's what that's about. All right, now back to our drugstore, our pharmacy. All right, for our pharmacy, we're going to have, as you might imagine, another breaker box. And that breaker box is going to do the same thing. It's going to distribute power. It's also called a main. In bigger buildings, it's called sometimes a main panel or main electrical panel. And so we're going to have a circuit here, and that circuit is going to go to the plug loads, the process loads, and it's going to have 120 volt hot wire, and it's going to have a neutral. And the electrons are going to go out this way, and they're going to go through the different electrical receptacles that may be serviced by this particular circuit and back. And if something's plugged in, they're also going to go through the equipment or lighting that's plugged into it. So let's say it's a, I don't know, make it a cash register for the pharmacy. That cash register needs to have its juice, and its juice is going to be 120 volt, and it's being serviced by that particular circuit. All right, then we need our lights, and so our lights are also going to be on a circuit, electrical circuit, and we'll send that out. Again, not surprisingly, it's going to be at 120 volt hot and a neutral. And maybe we have fluorescent lamps. Those are going to be powered by that circuit at 120 volts. All right, but now we have some equipment. So maybe we have an ice cream display. So we have a freezer, and it's always being opened, and we don't want it to get too cold, too warm when it gets open. So maybe it's like a commercial size display freezer. So when you go in the drugstore, you can buy some ice cream, and that one is going to have more power going to it. So what we're going to do for this one is we're going to send 3 hots and a neutral. Each of them is 120 volt. And this freezer then is actually not going to go, whereas this air conditioner here in the house, well, that one was 2 120s in phase. So it's going to give us 240 volts. This one is going to be 208 volts. More on that in a second. Actually, let's talk about that now. Why on earth, if we added 320 volts, would we get 208 volts? And the reason is because we would prefer for the equipment in here, the compressor in here that's keeping it cold, we don't want it to be loud, and we don't want to wear out the motor, and we don't want it to shake. And so we would prefer to have smoother power going to it. And one way we can do that is by staggering the electrons. So these electrons are moving out at the same time these are moving back, and these are moving out, And so they're all kind of staggered. All right, let's talk about some of the equipment that we are looking at. So when we say transformer, this is a transformer that might be next to a building. You can see it, usually you can tell the transformer because it has some way it needs to cool itself. And that's what's going to step down the power from, in our case, 12,000 volts down to 120 volts in these two examples. This is where it looks like when it's on a pole. This is a door to what it looks like when it's in a building. You can't really get in it usually. It's a pretty, with that many volts, because remember I told you high voltage means you're likely to get electrocuted. So with that many volts, they don't let people in like me to look around. You have to be in the know. And then these are the breakers. And so here are the breakers. In this particular case, these two breakers are ganged together in my house, and these go to the cooktop. So I have a cooktop and they go to the cooktop, and these two go to the oven. This goes to the sink side of something. This one goes to the upstairs bedroom. This one goes to the smoke detectors. This one goes to the coffee maker, and so forth. So each of those circuits is sending it out. And you can see this one has a GFI, ground fault interrupter, on the circuit. You can have ground fault interrupters on the electrical receptacles themselves if you're near a sink or a bathroom. But you also can have them on the whole circuit, and then you don't have to have the little buttons and ugly little receptacles. All right, and then this one actually is for a sub panel. So the one panel is going to then go out to a sub panel that's going to then go out to other things, like for an addition. And that's what happened in my house before I bought it. And then, each of these others goes somewhere else. And then, this is the air conditioner on the inside, the blower, the air handling unit. This is a compressor condenser unit on the outside. These were for the dryer, but there's a gas dryer now, so I guess I don't need 240 for that, because it's not trying to heat it up at the same time it's trying to spin it. Now this is the sub panel, and then so inside the sub panel you have the indoor unit, so that's the air handling unit in the attic, and there's the outdoor unit, that's the compressor condenser unit in the split system. And if you were here for previous 40 minutes of competence, you know what I'm talking about. This is baseboard heating, so it needs a little extra oomph as well. But this is just like a bathroom, and this is for outdoor. So there's like for outdoor electrical receptacle. All right. Now, to understand the difference between single phase and three phase, I'm going to play. This is single phase. So if we have single phase, we have a choir where everyone's singing at the same time. So I checked it beforehand and it worked, but not surprisingly, it doesn't work now. I guess on Zoom it doesn't work. I had this happen to me once before. But these are all a bunch of people in a choir, and they're singing. It's great use of an atrium space, and they're all singing. And as they sing, it gets louder and louder and louder because there are more and more and more of them singing. So if you have more people singing, it brings more oomph, but they're all together. Now, I'm going to see if I can play it on my other computer for a second. Nope, it's not there. All right. So anyhow, that's a choir and it's singing, and it gives you more oomph. Now, if you could imagine it, this is another choir, and these guys are singing "Row, row, row your boat," and so they're singing it in rounds. So they're singing "Row, row, row your boat gently down the sea," and the other group jumps in and goes "Row, row, row your boat," while the first group is going "Merrily, merrily, 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 life is but a dream." So they're singing in rounds. So they're all singing, but not together. They're singing staggered, and that's what we want to think about for the three-phase power. It's staggered, and the reason it's staggered is that it makes its motors run more smoothly when it's staggered, because there's never a point where the electrons are all changing directions. In the first example that I gave for the house, there's 220 volt lines lines that are going out, and because they're in phase, they all send the power out at the same time, the electrons out at the same time, and they all pull the current back at the same time. So the motor wears out quicker, is less efficient, and is noisier. But in a three-phase, it's more like this. So this was also Hey Jude by the Beatles, right? So it's like there's a point where I think Paul McCartney is saying Jude 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 while the choir's going na 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 and so forth. So that's the idea behind three phase. So if we have single phase power, if again on the y-axis is the voltage, so up to 120 volts, and then down to negative 120 volts, so it's pulling the electrons back, then up to positive 120 volts. And remember, the voltage is the pressure. It's how much pressure, how much is pushing those electrons through. And if we have two of them together, we have one that goes like this, but we add the second one and it goes even bigger. And because we describe it as 240 volts, even though for most of the time it is not 240 volts, it's something less. It maxes out at 240 volts. And for that reason, we call it 240 volt power. But if we have three-phase power, in this case, 208 volt three-phase power, that's what we have here, we actually have one going up and down, and then we have another pushing when the other one's pulling and pulling when the other one's pushing, and we have a third that's kind of in between the two. And between the three, you can kind of see intuitively that that is smoother delivery of power. What's not so obvious is that if we add these three phases together, we don't get 360 volts. We don't get 3 times 100. Oops. We don't get 3 times 120 volts equals 360. Instead, we get 120 times root 3 as the max. So when they get added together, the maximum becomes 208. And that bothers people because they think, how can 3 wires that are 120 be less voltage in total than 2 wires that are 120? But in reality, it's just less maximum voltage, but it's still more current. It's still more juice. It's still more watts. It's just less maximum voltage over time. And so that we call it 3 watt. We call that particular flavor of power delivery 120 volt / 208 volt 3-phase 4-wire power. All right. Now, finally, if we have a bigger building, let's say it's a big office building, we're going to have power coming in also at 12,000 volts or something like that from the municipality. And we're going to send it through a transformer. Also could be on a pole, but is likely on the ground next to the building, or it could be inside the building. And then from that, we're going to have 3 lines and a neutral. And the hot line, the line that's sending the electrons out and yanking them back, the first one is going to be 277 volts hot. The second one is going to be 277 volts hot. And the third one is going to be 277 volts hot. And then, of course, we have the neutral. And they're all going to go into a breaker box, a main panel. And that main panel is going to have the circuit that's going to charge your desktop at work. Maybe it doesn't charge, just plugs into your desktop at work. Well, that's going to be 277 volts. But, and a neutral, but our computer doesn't work on 277 volts. If you plugged your computer into 277 volts, it likely would break. So what we're going to do is we're going to have these micro transformers in and around the building that are going to step the voltage down again. And in this case, they're going to step it down to 120 volts. So we'll have 120 volt hot, and we'll have our neutral. And then we can have a normative electrical receptacle or an outlet. Electricians call them receptacles, so we'll call them receptacles. And that's going to, so if you have your computer and your CPU. These are going to plug in. These are going to plug into the electrical receptacles at 120 volts because that's how they operate. Now, we're going to have our lighting on another circuit, and for our lighting, we'll have our circuit breaker like before. But for our lighting, instead of delivering 120 volt for our lighting, we're going to deliver 277 volt hot to the lighting and a neutral for this branch circuit. Remember, the branch circuit is kind of the final circuit, and that's going to go off into fluorescent, or these days off in LED. And it's going to light it up. Now, why would we want to go 277 volt to the lighting? Well, the reason is because if we have a big old building, we have a lot of copper running through that building, just a lot of wire. And because watts equals volts times current, which means that the power is equal to the pressure times the wire size, because of that, we can, if we increase the voltage to get the same amount of power for the lighting, we can decrease the wire size. And by decreasing the wire size, then we have saved ourselves a bunch of money. It doesn't seem like it would be a big savings, but in a big building, it actually really adds up. Now you say, but wait a minute, the reason that we kept the voltage low before is so we wouldn't get electrocuted. Yes, that's true, but the idea is that your fingers really aren't going to be near, in normal circumstances, they're not going to be near these wires because they're going straight from the breaker box that you don't have access to as a regular person. Only your physical plant maintenance people have access, and it's going directly to the lighting, which you don't put your fingers near the wires in the lighting anyway. So there's less of a risk of getting electrocuted. So we don't mind having a little more electrical pressure, a little more voltage to go through if it means we can have thinner wires. Then for the elevator, we need a lot more, and we can't just bring that by having a thicker wire, because then that wire would get hot. If we need a lot of power and we have normal amount of voltage, then we have to make it up. Normal amount of pressure, we have to make it up, and we have to make it up with a bigger wire size, more current, more amperage. And so by doing that, we're risking fire from the wire getting hot. So what we're going to do is we're going to send 3 wires that are hot plus a neutral, and there's going to be a 277 volt hot, another 277 volt hot, and a third 277 volt hot, and of course a neutral. And these are also going to be 3-phase. So this particular flavor of power for a big building, this is for our office building, office tower, let's make it clear it's a big building, is going to be 277 volt. And when all 3 are together, it actually works out to be 480 volt, because 277 volt times root 3 with this 3-phase power is going to be 480. So our elevator is going to work on 480 volt. And our lighting is going to be working on 277 volt, and our plug loads are still going to be 120 volt. All right. And it's important. I used to think this was bogus, but it's actually kind of important. People have told me over the years of doing these seminars that they buy an elevator, they specify an elevator, and they accidentally pick one that's 277, or that's a 208 volt elevator, a 208 volt elevator. Well, it won't work on 480 volts. So you have to know the difference. You have to know what flavor your particular building has. Now, 277 volt, 480 volt, 3-phase, 4-wire power service. And the 4th wire, of course, is the neutral, just like before. So looking at what these things really look like, this is the micro transformer. So this is a transformer that's taking 277 volt power, and it's turning it into 120 volt power so that we can run our process loads, which is another fancy way of saying our plug loads. And this is the different types of power delivery kind of all mapped out. And before we go on, let me ask you another question. Go ahead and you're going to actually answer this to yourself. You have to commit to that. So this guy right here, how many phases is that? How many phases is that? Go ahead and answer to yourself. Answer aloud. Make sure you actually commit to it. If you said two phase, you're wrong. It's single phase. So there's only a certain amount of availability for power because we need to standardize all the equipment and electronics that we're plugging in and all the lighting that we're wiring up. And so it's either going to be 240, 120, 240, which is what this is, volt. And if it is, it's single phase. So whereas the three gang together were three phase, the two gang together are single phase. A bit of a trick there. All right, now I made some drawings of this. Let's see. They're not quite ready yet. they're just about ready. We're going to make a couple changes to them, but this is our house. And so to review, we have the power coming in from the power company. We have our two hots at 120 volts and our neutral. This gives us 120 volt or 240 volt single phase 3-wire building service. It's going to go into our breaker box. Now these should be ganged together, and actually I'm going to put them over here because right now they're flipped across, which means that the breaker box has detected that there's too much current going through the wire, so there may be a short, and the wire was heating up. So we can take those away here, and then we'll put the switch on this side so it's equal to the others, because they're all going to be in line if they're working. And this is going to be two in phase 120 volt lines is equal to 240 volts plus the neutral, and that is our air conditioning unit. This is our electric lighting and at 120 volt, and this is our processor plug loads. For the drugstore that we did, we have our from the power company, we actually would have 3 wires coming in. We have our hot at 120 volts each, 3 of them, and we have 120 volt 208 3-phase 4-wire service. See, this stuff is not that hard. It's kind of complicated, but once you get it, it's not that hard. Again, these should be ganged together, and I'm going to go ahead and gang it together on this side so that it looks like they're on. And so we have for the process loads, we have the hot 120 and the neutral going to the cash register. For the fluorescent lighting, we have the hot 120 and the neutral going to the wiring and for the lighting. And for the freezer, we have the 3 out of phase 120 volt hot wires, which are going to make 208 volts, strangely, and that's going to be our maximum. But it's going to smooth things out, make the motor in here more efficient, make the motor in there quieter, make it last longer because it'll move around less because it's got smoother power delivery. And finally, we have our large office tower, and our large office tower needs more oomph, so we're going to run more wires. We're going to run wires at a higher voltage to get us more oomph when we combine them for big things like an elevator that's going to take a bunch of people up, 30 floors. And to save wiring, we're going to use a special kind of lighting that's 277 volts. So if you look at a catalog, oftentimes they'll have 120 volt options and 277 volt options for the same fixture. And so that just depends on whether or not the building is made for 120 or 277. So if it's a big building, maybe 10,000 square feet or bigger, it may be 277. Now there's no fixed line between a small building and a big building, but if it's obviously a giant building, it's almost certainly going to have 277, 480. And if it's obviously a small building, it's almost certainly going to have 120, 208. All right, and then of course for our computer, we need 120 volts. But we don't have 120 volts coming in the building, so we're going to take the hot 277 and we're going to have transformers. And the extra cost of the transformers to step it down from 277 to 120 is going to be dwarfed by the savings in having smaller wire all around the building, which again doesn't seem like that could be, but it be. And this particular type of flavor is called 277 volt, 480 3-phase 4 wire. Now, this is all of it at once. If I'll pause it here, if you want to take a screenshot or if you want to take a phone photo for your own studying, I'll leave this up. Why didn't I just start with this? Well, because it turns out we learn at the pace that we draw. And so I could just show this to you, but it would be overwhelming if I didn't let it unfold, as it were. This is why Khan Academy is so effective. And this is why we spend the money to animate the Amber book. I mean, you know, the Amber book, if I was doing a normal video like some other people do, I mean, that would cost maybe 1/10 or even 1/15 the resources in terms of time and dollars that it takes to animate. So there's a significant amount of time that goes into animation and resources, but we do it because it's a better way to learn. It's more fun. You'll retain it for longer, and you'll be able to use it both for the exam and for your career. All right, for next week, this is your assignment. We're going to put these flooring options in order from most embodied energy to least embodied energy. So we have carpet, linoleum, rammed earth floor, stone tile, terrazzo tiles, wood, vinyl composite tiles, and commercial vinyl flooring. You can ignore that little period there. Commercial vinyl flooring. All right. Now, I am going to review from last week. All right. Last week, there was a question near the end about post-approval amendments. And I said I'd try to address this. I'd try to address it this week. And the question is, are those bulletins? So I did a little research, and whoever asked that question, if you're still on, let us know. But I'm pretty sure you're from New York, because this is a New York phrase. So the New York Department of Buildings has something called post-approval amendments. And it's for something like, oh, if you need to keep if you're trying to change the permitting, basically. So if you need to have your building permit for longer, or need to extend it or change the scope because something broke while you were trying to fix it, and so you need more scaffolding, or whatever the case may be for permitting, you need to redirect people on the sidewalk in a different way than you thought. Then you do a post-approval amendment, and that's with the Department of Buildings, not so much with the contractor. All right, chat questions from last week. Are bid bonds always required? The answer is no, they're not always required, but they're almost always required on big projects, and they're almost always required on public projects. Bid bonds, you'll remember, are the insurance policies that a contractor will be forced to take out, so that if he flakes out, then the owner gets paid the difference between his lowest bid and the next lowest bid. That way the owner still gets the project at the lowest bid cost, even if it's kind of a brilliant financial engineering scheme. Everyone comes out ahead because the owner has something he can trust, and the contractor has something that he can bring to the owner to reassure the owner. And of course, the cost of it is borne eventually by the owner, because eventually all the costs are passed on to the customer. So that's a problem, I guess, in the system, and inefficiency in the system. But it saves the trouble of having a contractor flake out when they realize that they underbid and they can't make a profit. All right. The next question we had is, would master spec be considered prescriptive specifications? No, not necessarily. Master spec is not so much the type of specifications, it's more like the cataloging system. So if you're old enough to have been taught this, it's like the Dewey Decimal System for cataloging books in the library. So it doesn't, just because it's in master spec doesn't mean it's a historical fiction book. It could be a fiction book, or it could be a nonfiction book, or it could be a self-help book, or anything. It's just cataloged in a certain way where the contractors and subcontractors and you, the architect, know where to look for something. So if you wanted to know whether it was 277 volt power or 120 volt power that was going to be delivered to the building, that's the kind of thing that would likely be in the specs. And those specs could be prescriptive, they could be performance, they could be proprietary, and likely they're combinations of all three. Even within the same spec, it may have a description about how it performs. They may say that it needs to provide, it needs to be, I don't know, it needs to provide continuous power at 277 volts, da 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 da. It needs to be made with a fluid that cools it down, that is fire resistant, and so forth. So it may talk about how it performs. It may be prescriptive in that it actually explains to the contractor how she's going to put it on a pad. So you will first, put it on a pad that will be made of this, and it could be proprietary in that it actually calls out a specific manufacturer and model number. The next question is, I see people memorizing the master spec division numbers and description. Do you think we should memorize that? No, I don't. I don't think it's a good use of your time. Wire modifications considered bidding documents if they were not yet known at the time of bidding. And so you see it's, the bidding documents kind of include everything. In reality, they probably don't include the modifications. They should probably come up here to the addenda and not be included in the modifications. So that's a good catch. I don't think that the bidding documents actually do include the modifications, although certainly the contract documents would. So the contract documents actually probably should come over here and include the modifications, and the bidding documents should not. All right, fire away.
Hi, Michael. There's two questions for
Hello.
me. One is on those 3-wire plus neutral or 3 wires plus neutral going to the equipment. Do they go to the equipment on separate, how do you call it, terminators?
No, they're all kind of bundled together.
Oh, at the end they bundle together too, huh? Okay.
Yeah, they're all kind of bundled. It's just a single. The electrician is just running one thing, but then at the end they split out. So yes, there's a bunch of wires that are sheathed, and then they all are bundled together and sheathed again. So you'd have, just like with the kind of wire you have that plugs into your electrical receptacle, it looks like this, and then each one of these is sheathed, and then that's sheathed in a common wrapper. The same thing would be true of 3-phase or anything. They're going to be individually sheathed, but they're going to be run together.
Okay, gotcha. The second one, why is it that most of Europe and Asia run 220 volts and US is the one having 120?
Right. So originally, actually, every building was different. So you would have a building on your block. Your block might be run with one type of flavor of power, and the next block might be a completely different. Your city may be alternating power, but the next city over may be direct current, and your city may be alternating current. It could be your block is alternating current, and the next block is direct current, and different voltages and everything. Eventually, they were standardized nationally. And as you might imagine, they weren't all standardized the exact same way. So if you're in the Middle East, it's one way. In Europe, if you're in the US, it's another way. So I guess it's just like anything else. It was a time when we were a bit less global. But let me ask you a question. I mean, why is it that your computer needs a charger that looks one way and creates a certain kind of voltage, and my computer is a different voltage for a different charger? Because I would love it if I went to a hotel for a business trip, and if I forgot my wire, I'd love to be able to just buy the wire or just borrow the hotel's wire, because I can't imagine that computers need wires that are that different. So things just don't get standardized. There's not interoperability or interchangeability as much as we would like, because the nature of innovation is such that things get made quickly, and then they don't really change. But if you were making the system from scratch, you would do it that way. But it is, I mean, because the voltage is higher in Europe, you're more likely to get electrocution, and probably for the same appliance, less likely to have a fire.
Safety, I guess.
What's that?
It could be safety factor, right?
Well, yeah, but it's a matter of safety of fire versus safety of electrocution. So it's a little bit of a trade-off always. But yeah.
Thank you.
You're welcome.
I guess I wrote mine in the chat, but I was wondering if you could talk a little bit about the relationship between the wires and the neutral and the way they're connected. Would you
Yeah, I'm
ever
glad you.
connect two wires and a neutral?
Yeah, so it's okay. So the electrons are moving out this way, and then they're going into the electrical receptacle, and they're going through the wire, through the motor, back on the neutral, back through the neutral, through the breaker box to the neutral, and then into the ground, which is kind of a weird thought. And this is different than the ground. So there's also a ground wire, but that's actually different. This is the neutral, which is grounded, not to be confused with the ground. And I talk about this quite a bit in the Amber book. But so the ground kind of acts as a reservoir. So all these electrons will be stored there, and then they'll be yanked back out of there and taken back through and back to the power company. And then they'll go back again the other way and into the ground, and then back again the other way, which seems like it's different than your battery. It's different than what you do with your battery. But that's what the neutral is for. Yeah, that's the idea. I know.
What's the ground for? Where does it go?
Ah, okay. So the ground, let's do it for this piece of equipment. So for this piece of equipment, there's a ground wire. I mean, there's a lot of power going into it, and you can imagine that the people who work at this convenience store in this drugstore, they're maybe not super knowledgeable about electrical issues, and they may be kind of rough with the freezer. So they may have to move the freezer all the time because there's a door behind it. So there's a door behind the freezer, and and the freezer is kind of on wheels, so they're always moving the freezer. And when they do, in the back of the freezer, there's a little grommet where the wire moves through to get to the back of the freezer. And every time they move it, they yank on the wire, and it kind of rubs and rubs and rubs against the grommet. So eventually, the hot wire is actually touching the metal back panel of this freezer. So now you have 120 volt times 3, or maybe just one of them is touching. Let's say one of them is touching. 120 volts is electrifying that back panel. So the whole thing is like a bare exposed wire. But because the wheels are rubber, it's not grounded. So the electrical breaker box does not know to flip off because it's not getting hot. But if you're mopping and you're back there and you're mopping and you're standing in a puddle of water and you go to move that freezer to get to the door behind it, and by moving it, you put your hand on that metal panel on the back of the freezer, you can imagine that metal panel of the freezer is gonna, especially if you're standing in water, it actually is gonna hold like 75 times more current and electricity wattage in there than it would take to kill you. So you could very well die from that kind of an everyday thing. So what we're gonna do is we're gonna have a fifth wire in there called a ground, and that's gonna go back directly to the ground. And the ground, instead of connecting to the motor in the freezer, is just going to connect to some metal portion of the freezer. That way, when the grommet first wore away at the wire, and this panel was first electrified, this panel is going to send electricity back into the ground, and the electricity is going to keep going out and into the ground, and the wire will get hotter and hotter, and this breaker will flip over, and you'll go to and the worker will go to the electrical panel and flip it back, and after a second it'll flip back again because it'll heat up again, and the worker will do it a third time and it'll flip back again, and then the worker's going to be like, huh, and the worker will call the manager, and the manager will call the electrician, and the electrician will come and realize that there's actually a problem back here that could be dangerous. So that's what the ground is.
Perfect.
Do you have a question, or was that your question?
Yes, no. Just going back to your analogy about the choir and the music, actually the instrument, and going back to the chart that you had here, the one with the waves. Would that be, yeah? Can you, if you can go back to that one right there? All right. So I'm trying to picture this in terms of is this each wave one instrument that is going on at the same time?
No, it's why I don't like to talk about electricity as a wave that much. No, think of the wave as your odometer for your car. Okay, your odometer goes like this. You know, your odometer. I'm sorry, your speedometer. Your speedometer tells you how fast you're going. It goes like this, but your car does not go like that. Your car doesn't go back and forth. Your car goes forward. So picture this like an odometer telling you how fast your car is going. Only it's telling you how hard, how much pressure there is at any given moment in the electrons. So the electrons are pulsing where they're going forward, and this is describing how much electrical pressure they are. And then they stop. So when it goes to here, it's actually zero. The electrons have stopped, because think about it. An electron is moving over and then it's moving back. And that means 120 times per second. I'm sorry. Yeah, it is 120 times per second because it's 60 hertz. So it goes back, it does one full cycle 60 times per second. It just happens to be 120. So ignore the fact that it happens to be also 120. It has nothing to do with that. But 120 times per second, the electron is going to stop and move the other direction. And so it's right here, it stopped, right here, it stopped, right here, it stopped. Here it's moving at this time, that's not a place, that's a time. At that time, it's like your odometer. At that time, your electrical pressure is maximized. And at this time, your electrical pressure is also maximized, but it's maximized going the other direction. And so what this is this is not a description of how your electrons are moving or any instruments. It's a description of the electrical pressure at any given moment in the wire. Does that make sense?
Yes, and so also in terms of the wires, these waves do not represent different wires. When you were talking about the 3 wires on the larger equipment, these waves, the one on the bottom, the 208 volt 3-phase.
Yeah. Yep.
Is each of those waves a different cable or?
Yeah. So each one is a different wire in the wire that's going around to the piece of equipment.
Got it. Thank you.
So if we look at the equipment, each one of those is a wire, and each one is pulling and pushing, but not all at the same time. So it would be like, I don't know. I mean, it would be like, I use the example of InPhase being a really elite prep school, boarding school at rowing. If you took a bunch of first graders rowing at a non-elite prep school and you had them rowing in a regatta, you can imagine that they would not all be rowing at the same time. And so that's kind of that's the way you need to be thinking about 3-phase power. They're not all some are pulling while some are pushing. And it seems like that would not work as well, but it does work as well because it's smoother at any given moment, because there's never that point, like I was talking about, there's never that point 120 times per second where the electron is changing directions and it's stopping. Because each time the electrons stop, the motor stops for a split second. And each time the motor stops, it jerks it forward just a tiny bit. So it makes the motor less efficient, it makes it less smooth. So your elevator is going to be choppier, your elevator is going to be noisier because things are rattling around, and your elevator is going to need more maintenance, and it's not going to last as long because it's rattling around.
And
Okay.
all those 4 wires are bundled together, right?
Yep.
Okay, great.
Why is there never a 2-phase?
I knew somebody was going to ask that. There's always somebody who asks that every time. Yeah. So no, you can't have a 2-phase. In the same reason there's not a 4 and a 5-phase. It's the same reason. Someone's music is on and it's getting picked up. So it's the same reason you can't have an infinite number of ice cream flavors at the parlor, at the ice cream parlor, and you can't have an infinite number of clothing options. Someone has to make it. So we make these different options, and there's actually two others. There's a smaller version for sheds and other outbuildings and temporary buildings, and there's a bigger version for like huge factories with really intense electrical processes where they're, you know, smelting down metal or something like that. That I didn't show. I didn't show either of those because they're a bit more rare. But we make these 5 choices, 3 I showed you plus 2 others that are not used often. We make these 5 choices because we have figured out that they are the best fit. And for those of you guys who watch my video, it's Tesla who had kind of decided on 3 because he was obsessed with 3. We make these 3 phases because 3 makes it so that at no time it's smooth enough. It's smooth enough that it smooths out the equipment, but it's not so many wires that it takes forever to put it together. But plus, I mean, Nikola Tesla, who kind of invented this, he was obsessed with 3, so he would do everything with 3. So if he knocked on the door, he'd knock 3 times. You know, penny, penny, penny. You know, he'd knock 3 times always. And if he was checking the stove to make sure he turned it off and it wasn't hot, he would need to touch it 3 times. He was OCD in that way. And so it's probably the main reason there's 3 and not 2 is because Nikola Tesla was obsessed with 3. But also it's proven to be a pretty good model for balancing the complexity of multiple wires, and not just multiple wires for the electrician, also for the equipment, you know, within the motor itself, and the smoothness. But you could have, you know, but there's always some, you know, yes, you could have 2-phase, you could make it, but you'd have to make it in like an electrical engineer's lab. It's not something that you can run any equipment on, because if we had an unlimited number of choices, then our equipment wouldn't work unless it happened to work with exactly that available power. So if we had 5-phase 94 volt, if we had 5-phase 94 volt, then we would have to make blenders and freezers and air conditioning units and computer printers and iPhone chargers. We would have to make all of them at that particular flavor. And then if you had something different, then we'd have to make different equipment for the different flavor. And if you want to look on your charger right now, like your charger has a big thing like a snake that swallowed a pig, python that swallowed a pig, has a big lump in it. Sometimes the lump is halfway between, sometimes it's all the way on one end near where you plug it in, like on Apple products. But if you look at the fine print on that, you can see the transformer that it has, you know, has this much voltage coming in and this much voltage going out. So it's actually the alternating current going in at 120 volts. But your transformer, if you want to look at it now, go ahead, take the effort and look at it. If you want to look at it now, you'll see the transformer actually has a range of voltages. And that's because people get really pissed when they plug in their computer in Europe and it breaks their computer. So, so you can make equipment that works with a range of voltages. So it probably says 120 or 100 to 240 volts. So it can handle anything down to 100 or anything up to 240, or maybe it says 120 to 240 or something like that, because that way, if you plug it in Europe, it won't break your computer. And then it says the output, and the output may be, and the input's alternating current, but the output may be, you know, 4.7 volt direct current or 6.1 volt direct current or something like that. So that itself is a transformer. And it also changes AC current to DC current, which is called a rectifier. All right, guys, good night and get licensed.